Hello, my name is Shannon Clayton, and I would like to present my tsunami warning system. In 2004, one of the deadliest tsunamis in recent history decimated populations in the Indian Ocean. Among them were people who lived on an island called Sri Lanka. They had no warning, which led to the deaths of over 200,000 people. My design question for this internship is, how can I design an effective tsunami warning system for the people of Sri Lanka? There were 3 criteria that I needed to keep in mind as I was designing this warning system. First, I needed to make sure that I gave enough warning time, which is important because it'll give people time to get to higher ground. Secondly, minimal false alarms is important because a high number of false alarms may cause people to ignore the warnings and ultimately put them in danger. And lastly, I needed to make sure that I kept the cost minimal. The money for the warning system comes from the same account as schools, bridges, and roads, so I had to make sure to keep the cost low. In order to help you understand the science behind tsunamis, you need to understand how they relate to convergent plate boundaries, underwater earthquakes, and energy. During plate motion at convergent plate boundaries, one plate will slide under another. This is called subduction. Earthquakes at or near convergent plate boundaries underwater will be the ones most likely to cause a tsunami. But remember, all earthquakes don't cause a tsunami. Lastly, energy is related to tsunamis because during my research, I learned that there are 3 different types of sensors which I could use in my design. There are earthquake, shallow, and deep sensors. I had to consider both the pros and cons of each sensors so I could use them in my design. Let me tell you about them here. I used this information that I learned during my research phase, plus this map of the Indian Ocean, to decide where to place my sensors when I was ready to start testing. Since tsunamis only happen at convergent plate boundaries, I know that I want to focus on the areas that I marked in purple on my map. Also, I wanted to focus only on the earthquakes that caused ocean-wide tsunamis, and those are marked as solid circles in my map. For my first test, I just wanted to see what kind of data I would receive if I placed one of each type of sensor in an area where I knew that there were convergent plate boundaries and ocean-wide earthquakes. Not ocean-wide earthquakes, ocean-wide earthquakes that caused ocean-wide tsunamis. I placed one of each type of sensor in these locations. The data I collected indicated that although I had 0 false alarms, I only had a warning time of 17 minutes, and not all the warnings were being received, which was not a good thing. After several more tests in which I tried different combinations of sensors, I submitted my 5th version to Hannah for feedback. You can see on the map that I included 1 earthquake design, which I placed on land, 1 shallow sensor, and 5 deep sensors. Hannah suggested that I increase my warning times by using more earthquake and or shallow sensors. And then she also said that I needed to omit any unnecessary deep sensors. So I had to examine my earthquake to see which ones were not being used. During my design phase, I realized how difficult it was to place equal importance on all 3 criteria. I decided I needed to have a trade-off. In my opinion, it was most important to prioritize warning time and cost, because first of all, I need to make sure everyone had enough time to get to higher ground. And secondly, I want to make sure that the cost was low enough so it wouldn't affect the money set aside for schools, bridges, or roads. I mean, after all, if people need to evacuate, they need good roads to travel on. This means that the least important criteria for me was the number of false alarms. I would try to keep it low, but I felt I could justify a handful of false alarms over a 50-year period. After a few more tests, I had my 8th version, which ended up being my best or optimal design. This is the design that I would like to propose to you for consideration. It is my best version because it had the highest warning time and the lowest cost. You can see that I used 1 earthquake sensor, 3 shallow, and 3 deep sensors. P.S. There's supposed to be a picture on this one. That's the picture that's supposed to be on that one. I forgot to put it on there. Don't forget to put it on there. The data for my best or optimum design was good. After I received Hannah's feedback, I made a goal of 50 to 60 minutes for my warning time. My actual warning time was 67.25 minutes. Now, I did have a test where my warning time was 75 minutes, but the cost was way too high. And since that was one of the criteria that was most important for me, I didn't use that design. After I received Hannah's feedback, I made a goal of 0 to 1 false alarms, but actually I had 3 false alarms. I did have a test where I only had 1 false alarm, but again, the cost was way too high. I was really committed to keeping my costs down, so I didn't use that design. And finally, after I made a goal of trying to keep the total 50-year cost to $84 million, my optimal design came in just under my goal at $83,306,000. I didn't have any other designs that were cheaper, which is another reason why this is my best design. Let me take one last opportunity to summarize my plan and explain why my design is the best tsunami warning system for Sri Lanka. First, it offers a maximum warning time of 67.25 minutes, plenty of time for people to move to higher ground. Secondly, the total 50-year cost is only $83,306,000. In my opinion, this would not take away a lot of money from schools, roads, or bridges. Now, I realize there's an average of 3 false alarms, which may seem a little bit high, but I don't think that's a significant number. Only 3 alarms or false alarms in 50 years, I think we can justify that. Thank you so much for listening to me, and let me know if you have any questions.